In this video, let's talk about naive Bayes, which is a classification problem. Now let's take an experiment rolling a dice. We all know that dice has 6 values 1, 2, 3, 4, 5 and 6. Now probability of getting a value 1 will have 1 by 6 chance. Probability of getting the value 2 will also have 1 by 6 chance, and so on. Probability of getting the value 6 also will have 1 by 6 chance. This is because these are all independent events. Now let's talk about something interesting called dependent events. So let's experiment here by taking a bag of marbles here. Okay, let's have a bag of marbles. Let's say we have 3 red marbles and 2 green marbles. Okay, probability of taking out the red marble will be total 5 marbles here and 3 red marbles here. Now the probability of taking out the red marble will be 3 by 5th chance. And in the next event, the probability of taking out the green marble will be, we have now total 4 marbles because we have already taken out the red. That's why these are dependent events. Now probability of taking out the green marble will be equal to, we have 2 green marbles. Now here I can write in this probability of green given red. So after taking out the red, the probability of taking out the green marble will have a chance of 2 by 4th. Right. Now here I would like to put the conditional probability formula. Let's see how I can do that. Probability of red and green marbles will be equal to probability of red multiplied by probability of green given red. Now, similarly, I just wanted to take out in the next case, what I would like to do it here as a fresh again. This time, for the first time, I wanted to take out the green marble from this bag. Okay, so let's write for that. Probability of taking out the green from this bag will be, we have 5 marbles. Out of 5 marbles, we have 2 green marbles. So it will be 2 by 5. Now in the next event, I wanted to take out the red marble. Okay, red marble. This time given green. Okay, given green, which will be equal to, now we have overall 4 marbles here, and out of 4 we have 3 red marbles, right? So 3 red marbles. So here also I can write probability of green and red must be equal to probability of green multiplied by probability of red given green. So I can put this formula as like this. Now this equation is called conditional probability. These both equations are called as conditional probability. Now here what I would like to do here is, see, now if I wanted to put this formula in this, I will have something like this: 3 by 5 multiplied by 2 by 4. Okay, now if I put these values into this formula, I will have 2 by 5 multiplied by 3 by 4. Now this value and this value must be equal. Okay, so this is proved that this and this must be equal. Now I can put directly here saying that P of red and green must be equal to P of red and green must be equal to P of green and red. Now wanted to put in terms of formula here. Okay, here I would like to write here P of red multiplied by P of G given red. I'm just putting this here. Okay, I'm just putting this as this here. Okay, is equal to P of green multiplied by P of red given green. So normally we don't use red marble and green marble here, but generally we use A and B letters. So what I would like to do is I would like to convert this R and G to A and B. Let me just put here R to A and green to B. I wanted to substitute this to get, as a standard formula. Now probability of, in case of R, I wanted to put A multiplied by probability of B given A is equal to probability of B multiplied by probability of A given B. Right? Now I can write like this, right? So let's see what we can do with this. Now here I wanted to pull this out so that I wanted to make the formula very clear. Probability of B given A must be equal to probability of B multiplied by probability of A given B divided by probability of A, and this is called, this is our Naive Bayes theorem. This is the crux behind our Naive Bayes algorithm. This is our Naive Bayes theorem. Now let's take a simple example here. Let's take a simple example. Let me just write let me just say that I have a features called x1, x2, x3 and so on xn. These are all my input features. Okay, these are all my input features. Now I also have an output feature here. Okay, here y as an output feature. In output feature, based on this several inputs, we'll be saying that yes or no. Okay, so depending on the different rows here. Now here I wanted to put this in this formula. Okay, here we have an output here. Okay, probability of output y given the values input x1, x2, x3, x4, x5, okay, and so on xn is equal to probability of, I can write according to this formula as probability of y multiplied by probability of x1, right, probability of x1 comma x2 comma and so on xn given output y. I can put it in this way, right? And similarly on the bottom I can say probability of x1 comma x2 comma x3 and so on xn. I'm just putting this example as per this equation. Okay, now further I wanted to just put it in a simplified way. Okay, here I wanted to write here probability, I just wanted to rewrite this equation here. Okay, probability of y multiplied by probability of x1 for a given output y1. Okay, I can write like this, right? Now probability of x2, because for different inputs you'll get different outputs. Probability of x2 given output y2 and so on. Probability of xn given yn. As a whole I will write this probability of x1 multiplied by probability of x2 multiplied by so on probability of xn. I can write this equation as like this. Now here I wanted to further make you very simplify. I wanted to take very simple data set here. Let's say that we have a data set here. Okay, we have a data set here. Okay, let's say that we have only four features in the input. Okay, x2, x3, x4. We have this only four features. Okay, and we have also output feature here. Depending on this variables, we are just saying that it is yes or no. Right. Now, here comes the interesting part. Now, let's say that the probability of y when it is equal to yes, okay? Given input xi, which will be equal to, I can write this equation as probability of yes multiplied by probability of x1 given y is equal to s, okay, yes multiplied by probability of x2 given s multiplied by probability of x3 given yes multiplied by probability of x4 given yes, the whole divides by probability of x1 multiplied by, and so let me write completely, probability of x4, okay. Now we have this here. Similarly, we can also write probability of y is equal to no, okay, y is equal to no for the given input xi, which will be equal to probability of no multiplied by probability of x1 given no multiplied by probability of x2 given no multiplied by probability of x3 given no multiplied by probability of x4 given no, and the whole we are just dividing it with probability of x1 multiplied by probability of x2 multiplied by probability of x3 multiplied by probability of x4. Now here you can see that in our numerator we have something called a scalar value which is constant, it can be fixed, right, and which in our later equations we are trying to ignore this constant, and the same thing here also, we are not going to put this in our equations later on, okay, this we are trying to ignore, this we are trying to ignore, okay. Now let's talk about some of the assumptions. Let's say that we have got yes, let's say probability of yes by giving given input x, we have got some value here. For this, after applying some based on the example, let's assume that we have got something called 0.13 here, okay, and similarly we have got for probability of no also we have got some value, let's say, which is equal to some 0.05, okay. Now in the coming videos I'll take the practical example. For now I'm just talking about the problem statement, just a little example to understand. Now we all know that our hypothesis, when it is greater than or equal to when it is greater than or equal to zero point 0.5, then it is true, which will be represented as 1. When it is less than zero point 0.5, then it is represented as 0, right? This is what we have. Now here I wanted to normalize this. To normalize this, I wanted to write here, okay, to normalize this, I wanted to put this equation in this way. Probability of S by the given input xi must be equal to 0.13 divides with 0.13 plus 0.05, which is equal to 0.72, which is 72%. So it is 72% yes, which is 72% yes. Now similarly we can also normalize for probability of no for the given input, probability of no for the given input xi. We can also get here we can also write this way, 0.13 plus 0.05, which will be around 0.28, which is 28% no, right. This we can also write it as 1 minus probability of s for given xi, then also we'll get the same 28%. All right, this is actually behind naive Bayes algorithm. So this is a basic. In the next video, I'll try to see the real example how we can actually calculate. All right, this is it in this video. We'll see you in the next one.